Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Yield Surface, and it is going to introduce how to draw the yield surface for failure series. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the yield surface of von Mises, Mohr-Coulomb, and Drucker-Pragger. A yield surface is the representation of a failure theory in the principal stress space, which sounds more complicated than it actually is. To keep things simple, let's start by considering a plane stress case, where one of the three principal stresses is equal to 0. By convention, principal stresses are ordered from largest to smallest, like this. But since we don't know yet how the stresses will be ordered, I will refer to them as sigma A, sigma B, and sigma C instead. We will say sigma C is equal to 0, and so the two axes of our yield surface graph correspond to the two non-zero principal stresses, sigma A and sigma B. Now we start with ductile materials. The yield surface for the maximum principal stress theory is easy to plot. We call it Rankine yield criteria. It says that yielding begins when either of these principal stresses is equal to the yield strength of the material. So it looks like this. Yielding is considered to have occurred when the stress state reaches this line. Next, let's plot the yield surface for the Triska theory. This theory states that yielding occurs when the difference between the maximum and minimum principal stresses is equal to the yield strength of the material. But it is not as simple as taking the difference between sigma A and sigma B. Plane stress is still a three-dimensional stress state. In the top right quadrant of the graph, both sigma A and sigma B are positive, and so sigma C, which is equal to 0, is the minimum principal stress. The yield surface looks like this. But in the bottom right quadrant, sigma B is negative, and so sigma B is the minimum principal stress. That gives us a yield surface that looks like this. Repeating this process for the other two quadrants completes the Triska yield surface. Von Mises yield theory for plane stress conditions is defined using this equation when expressed in terms of the principal stresses. We can square both sides of the equation and see that it is of the same form as an ellipse, which gives us the von Mises yield surface. Let's plot some experimental data for tests performed on ductile materials and see how each of these theories compares. It is clear that the maximum principal stress theory has large areas where its use is potentially unsafe. So let's get rid of it and compare Triska and von Mises. Both agree well with experimental observations, although von Mises agrees slightly better. The Triska yield surface lies entirely inside the von Mises surface, meaning that Triska is more conservative. If we assume that the principal stresses will increase in proportion to one another as a load is applied, and so the stress paths are straight lines, the difference between the Triska and von Mises series is largest for these three configurations. The maximum difference between the two series can be calculated to be 15.5%. Von Mises is usually preferred to Triska because it agrees better with experimental data, but Triska is sometimes used because it is easier to apply and it is more conservative. So far, we have looked at a plane stress case with sigma C equal to 0. But for a general three-dimensional stress state, sigma C will be non-zero. We know that the Triska and von Mises yield surfaces are not affected by hydrostatic stresses, And so to obtain the yield surfaces in 3 dimensions, we just need to extend the plane stress yield surfaces along the hydrostatic axis. For brittle materials, the materials tend to have compressive strengths that are much larger than their tensile strengths. To assess failure of brittle materials, we need to know 2 separate ultimate strengths, for tension and for compression. Mohr-Coulomb theory is a failure theory often used for brittle materials. The plane stress failure for Mohr-Coulomb theory looks like this. As you can see, it doesn't agree particularly with experimental data in the bottom right quadrant. Modified Mohr theory is a slight variation on the theory, which better fits experimental data. It is one of the preferred general failure theories for brittle materials. Because failure theories for brittle materials need to account for the effect of hydrostatic stresses, these failure theories converge to a point when extended along the hydrostatic axis. However, Mohr-Coulomb yield criterion contains sharp edges, which introduces some difficulties in the implementation of the criterion for numerical analysis purposes. We will introduce the Drucker-Prager yield criterion to obtain smooth yield surface. The Drucker-Prager yield function can be written in terms of the principal stresses as this equation, where alpha and k are positive constants at each point of the material. J1 is the sum of the principal stresses. J2 is the second invariant of the stress deviation. If alpha is equal to 0, the yield surface in principal stress state is a right circular cylinder for the von Mises criterion. For alpha is larger than 0, the surface is a right circular cone with its axis equally inclined to the coordinate axis. If sigma ut is the tensile yield stress and sigma uc is the compressive yield stress, the Drucker-Prager criterion implies the 2 equations. Since the Drucker-Prager yield surface is a smooth version of the Mohr-Coulomb yield surface, it is often expressed in terms of the cohesion C and the angle of material internal friction phi that are used to describe the Mohr-Coulomb yield surface. If we assume that the Drucker-Prager yield surface circumscribes the Mohr-Coulomb yield surface, then the expressions for alpha and k are shown here. Now we can use the Drucker-Prager function to draw the yield surface. The right-hand side shows a section of the yield surface by the pi plane. From conclusions, what we learned? A yield surface is a 5-dimensional surface in the 6-dimensional space of stresses. The yield surface is usually convex, and the state of stress of inside the yield surface is elastic. When the stress state lies on the surface, the material is said to have reached its yield point, and the material is said to have become plastic. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.